Well, this is a culmination of a search which has been going on for some time now. It is going to be an achievement, I trust, which results in the verification to a very high degree of accuracy, what we call the standard model. This missing scalar boson has been perplexing us for some time, and the fact that the data now seem to say that we're on the threshold of a major discovery is incredibly gratifying and exciting to be here, and gratifying because I've had the privilege of being associated with this. It is very exciting and very commendable. It shows that the people who put this machine together did an excellent job, and some of my colleagues have remarked about how amazingly trouble-free this machine has been. And Jerry Grelnick and I go back 50-plus years. We learned our physics together, and we've talked physics a whole lot over the decades, both as undergraduates, graduates, postdocs, and beyond. And in 1964, I went to Imperial College, where he was located, and Kibble was a slightly more senior person there. And we knew that there were big problems with the so-called Goldstone theorem. Goldstone theorem was something which had hobbled efforts to construct the electroweak interaction theory. Weinberg is my source on this, and in his Nobel lecture he refers to the fact that when he tried to unify the theory of weak and electromagnetic interactions, it was a very difficult thing to do because of the fact that the models which he would come up with would have an excess of zero mass particles. And these are very difficult to accommodate. Other than the photon, we just don't have them sitting around too much. So he confesses to being very upset and very discouraged in the search for the electroweak theory. But then our work came along, the broken symmetry work, which enabled one to get rid of these zero mass particles. And once that was done, he unified the electromagnetic field and the weak interaction theory, and came up with a beautiful theory which only a few years later was verified by the discovery of the W and Z particles and led to a nice set of Nobel Prizes. So it was very satisfying to see things like that happen back in the 70s. And fortunately, there was still something in our theory which had yet to be checked out, and that was the excessive boson, the scalar boson, which is now being searched for. And one of the lucky things, as far as I'm concerned, is the fact that first, I've been privileged to have enough years added to my life to see this thing more or less come to fruition. And another thing is the fact that we did this back in the 60s. We assumed a very simple model. And physicists like to do that. Don't complicate things at the outset. You can put the complications in later. Display the underlying physics by means of a simple model. And so that was a model which had just a single scalar boson floating around at the end. And lo and behold, when the LHC zeroed in on this, it turned out that, yes, the single boson interpretation does seem to be okay. Now, I don't want to say that we have the final answer at hand, but it's very encouraging and very exciting that nature has picked the same example which we used 50-some years ago, and that we don't have to wait for more complicated versions of this theory to be checked out.